Hi, this is Nikhil Pembadi and this is teammate Hrutik. Okay, today I am presenting our final project for CS 8530 Advanced Operating System at University of Nebraska Omaha. Our project is titled Energy Aware Real-Time Scheduling for Autonomous Vehicle Sensor Task, and the central contribution is a novel mechanism we call the Dynamic Alpha Controller or DAC. So the four numbers you see on this slide are what we achieved with real hardware: 13,208 jobs measured, 0 deadlines, a 20 times improvement in non-critical task timing jitter, and up to 25% energy savings, all from a system that runs on any standard Linux machine with no kernel modifications. And let's dive into the agenda slide. So here what we see on the screen: introduction and motivation, background and prior work, system architecture, and dynamic alpha controller. Here is our roadmap for the next 20 minutes. We'll start with the problem motivation, build up the technical background, walk through the DAC design, show you the experimental results, and discuss the challenges we faced and how we solved them, and close with our future work. And here are the last four included in our agenda: experimental setup, results and analysis, challenges and design evaluation, future work, and conclusion. And the most interesting parts are slide 6 through slide 13, which includes the DAC state machine, the results, and the energy analysis. So I'll spend the most time there. So let's coming to the introduction and motivation. So let's start with the problem. Autonomous vehicles are not just a software challenge, they are an energy challenge. Research from Saifullah shows that computing hardware in a self-driving car already consumes about 41% of the total vehicle energy. In 2023 IEEE micropaper by Sudhakar projected that if AVs are deployed globally at scale, their computing workload could generate as much as CO2 as every existing data center in the world, unless each vehicle keeps its up compute budget below 1.2 kilowatts. And at the same time, these vehicles run safety critical control loops that must hit hard real-time deadlines. A missed deadline in the vehicle control task, which runs at 1000 hertz, could de-establish the vehicle. So we have a fundamental tension: energy savings versus timing safety. So our first two reports show that we can save up to 20 to 25% energy by reducing non-critical task computation to a static fraction, computation time utilization of their worst case execution time. But the keyword is static. That alpha was chosen offline before the experiment. In a real-time deployment, road conditions and sensor loads vary. A fixed alpha of 0.60 keeps suppressing computation even when the system is nearly saturated, which risks deadline misses. The dynamic alpha controller solves this. It measures load at runtime and adjusts alpha automatically. So let's dive into the background, Linux real-time scheduling. So to understand how DAC works, you need a quick background on the two Linux scheduling policies we use. So schedule FIFO uses fixed priorities 1 through 99. Liu and Leland proved in 1973 that rate monotonic assignment, higher frequency gets higher priority, is optimal for fixed priority scheduling with a theoretical bound of 69%. So the second one, the schedule deadline introduced in Linux 3.14, implements earliest deadline first combined with a constant bandwidth server. Each task declares three parameters: a runtime budget Q, a relative deadline D, and a period P. The kernel guarantees the task gets Q CPU units within every D-length window. EDF achieves 100% utilization on a single core, and crucially, the CBS provides temporal isolation. If a non-critical task overruns its budget, the kernel throttles it rather than letting it steal time from other tasks. So on the right you can see the energy aware prior work, RTDVS, DRA, and grub PA, all the achieved significant energy savings, but they either required kernel patches, ARM specific hardware, or only ran in simulation. Our DAC closes this gap with a fully user space POSIX implementation on standard Linux. So let's take a look at the slide 5, system architecture and task model. Our workload models the sensor fusion pipeline of a level 4 autonomous vehicle. We have a 5 periodic task. The 3 safety critical task, vehicle control at 100 Hz, lidar processing at 20 Hz, and radar fusion at 20 Hz, have their computation factor hard-coded at alpha equal to 1.0 at compile time. No code path in the DAC controller can ever touch these tasks. This is a compile time enforcement, not just a policy. The 2 non-critical tasks, they are camera processing at 10 Hz and path planning at 5 Hz, are the targets of DAC modulation. DAC adjusts their CBS runtime budget, leaving the response to observed load. A key design choice is the CBS headroom factor of 1.205. This satisfies the Linux admission control condition. 1.205 times 0.805 equals to 0.970, which is below the single core limit of 1.0. We verify this empirically. Every schedule set call succeeded without rejection across all 3 trials. And here is the elegant part of the pure EDF architecture. So our SC tasks have 10 and 50 millisecond periods. Their deadlines arrive far more frequently than 100 and 200 millisecond non-critical task. Under EDF, the scheduler always runs the task with earliest deadline. So our standard critical task naturally preempt non-critical task with 0 explicit priority numbers needed. So let's dive into the slide 6. So DAC state machine. So now let's get to the core of our contribution, the dynamic alpha controller. The left side shows the 3-state finite automation. Aggressive states alpha equal to 0.60 when utilization rho is below 0.67. Maximum energy savings at low load. Balanced states alpha equal to 0.80 in the mid range. Performance restores alpha equal to 1 when rho exceeds 0.87. This is safety rollback. The 5% hysterious bands are critical. Instead of transitioning from aggressive to balanced at the same threshold in both directions, we use 0.67 to enter and 0.7 to exit. This prevents the controller from oscillating rapidly when rho hovers near a boundary, which would cause repeated CBS budget renegotiations and increased jitter. On the right, the 5-step algorithm. The DAC controller runs as a scheduled FIFO priority 98 thread. Above all scheduled deadline task is the supervisor hierarchy. It waits every 500 milliseconds, reads the per task CPU busy time from a mutex protected accumulator, computes rho, applies the transition functions, and if a transition occurs, calls scheduled setarter. And on each non-critical task threads kernel, TID to update their CBS runtime immediately. The 500 millisecond window covers 50 vehicle control activations and 2 to 5 activations of the longer period task, giving a statistically stable row estimate while remaining responsive to load changes. So coming to the DAC runtime verification, these are the real measurements from our running system. Figure 1 shows the mid trial. Each blue dot is the observed row from the 500 millisecond window. The green step function shows the alpha DAC selected. You can see the row oscillating between 0.703 and 0.804 through the trial. The controller stayed in the balanced state the entire time. Critically, row dipped close to 0.72 threshold several times, but never crossed it. Exactly was the hysteresis band in the design to prevent. And the figure 6 on the right gives the cross trial view. Each trial spent 100% of its non-critical activation in exactly one DAC state. Aggressive for low, balanced for mid, performance for high, and the row ranges on the right show each trial's operating band fits entirely within the hysteresis zone with no excursion across boundaries. So let's coming to the experimental setup. Our experiments ran on Ubuntu 22.04.3 with Linux kernel 5.15 inside Parallels Desktop 19 on a Apple M series host with all three threads pinned to a single CPU core. We pinned everything to a single core so that EDF scheduling theory we use, which is proven for non-uniprocessor systems, directly applies to our experiment. CPU 1 specifically because CPU 0 handles system interrupts and would add noise to our measurements. Two system prerequisites: we disable the RT throttle by default Linux caps, RT task at 95% CPU, which would interfere with high utilization trials, and we granted caps is nice to allow scheduled statutory calls from non-root processes. We ran 3 control trials targeting different utilization regimes: low at row equal to 0.448, mid at 0.753, high at 0.912. Each trial run for 35 seconds to 5 seconds of warm up excluded from analysis, then 30 seconds of measurement. We lagged per job CSV records with nanosecond timestamps for offline analysis in Python. So our evaluation metrics are deadline miss rate, mean, and P99 response time, time jitter CV, where our safety invariant requires vehicle control CV below 1%, and estimated energy from 2-component power model. So the next half would be continued by our teammate Hrutik.
Hello, I'm Hrutik and now I'm going to take over the presentation from Nikhil. So this is our slide and now I'm going to discuss about our key results, about our zero deadline misses. So we have zero deadline misses across all 13,208 jobs in all 3 trials. So let me put that in perspective. So in our DAC version 2, before we fixed the scheduling architecture, vehicle control was missing around 293 to 450 deadlines per trial. So with a CV exceeding of 114%. So with the pure EDF CBS architecture of DAC version 3, we achieved perfect schedulability at every operating point DAC was designed for. So coming to the figure 2. So figure 2 shows mean response time with plus, minus and 1 standard deviation. So all 5 tasks stayed within their deadlines at all 3 utilization levels, as you can see. So the SC error, so safety critical task error bars are invisible at these scales. So this means their variance is essentially 0. And the safety margins are pretty impressive over here, as you can see in the graph. So in vehicle control, maximum response time was around 3.5 milliseconds against a 10 millisecond deadline, so which is around 64.9% margin. And coming to the path planning, so percentile 99th percentile P was 36 milliseconds against 200 milliseconds, so which is around 82% of the margin. So coming to the next slide, so next slide we are going to focus about safety invariant and vehicle control CV. So the primary safety criteria for this project was keeping vehicle control timing the jitter, so measured as the coefficient of variation, so it is below 1%. So a 1% coefficient of variation on a 10 millisecond period corresponds to 100 microseconds of standard deviation, which is within the tolerance of commercial brake actuators. So we achieved a coefficient of variation of 0.033% in low and 0.014 in mid and 0.008% in high. So the safety margins of 30, 71 and 125 times below the threshold respectively. So notice the interesting trend. So CV decreases, so CV means that the coefficient of variation decreases as load increases. So this is actually EDF determinism at work. So whenever there is an high utilization, DEC selects alpha CPU utilizations at 1 and vehicle control executes it at full declared wait time period every period. So with near zero variance. So the higher the load, the more deterministic the safety critical task execution becomes. So coming to the next slide, so CBS isolation, so which is 20 times non-critical task improvement we have achieved here. So this slide shows one of the most technically interesting results that we have achieved. So why switching from scheduled first in first out to scheduled deadline improved non-critical task jitter by 20 times. Yes, it's 20 times. So under scheduled FIFO, our version 1 baseline, so we have implemented this in our Parallels desktop, which is running inside our Apple Mac, Apple Silicon, which is Apple Silicon M series. So the Parallels hypervisor would occasionally preempt our virtual machine for 1 to 4 milliseconds mid busy wait. So because of scheduled FIFO count, wall clock time, this preemption influenced the measured response time to the full wait time. So camera processing showed a bimodal distribution. So either you're finishing at 9.6 milliseconds or inflating at 12 milliseconds, as you can see. So which is producing a coefficient of variation of 12 around 12.1, 12.0 to 12.1%. And under CBS in DAC version 3, the kernel maintains a CPU time budget, not a wall clock budget. So when the hypervisor preempts the virtual machine, the CBS accounting pauses the task timer. So when the virtual machine resumes, the task continues from where it left off. So the hypervisor preemption is observed transparently, and response times concentrate tightly around CPU utilization times of I. So which in the result, we can see the camera processing CV dropped from 12% to all around 0.6% in mid trial. So a 20 times improvement. This is not from changing any scheduling parameters, it's purely from CBS isolation mechanism. So moving on to the next slide. So in this slide we can see the box plots and coefficient of variation summary that we have achieved in this. So the box plot on the left confirm three things. First one, in the high trial, radar fusion achieves CV of 0.000% with a standard deviation of 0 at 4 decimal places. So this perfectly deterministic CBS execution. And second, so NC task median scale proportionality with CPU utilization, that is alpha. So camera processing medians are 4.4, 9.6 and 14 milliseconds across the 3 trials. So given that the low trial used 7 milliseconds, which is wait time for camera, and this correspond exactly to 0.6 into 7 and 0.8 into 12 and 1 into 14. So this is what DSC is correctly translating our utilization transitions into proportional computation reductions. So coming to the third one, and this will explain on the next slide, LiDAR and radar show elevated CV in the low trial. So that's an EDF co-activation artifact, not a bug, and it produced 0 deadlines misses. And moving on to the next slide, So here we are going to show about our energy savings that we have achieved. So the energy model is period of alpha equal to dynamic power times and power leakage. So where dynamic power is 2 watts and the leakage is 1.2 watts from the Jetson AGX Xavier dataset. So the bar chart shows estimated energy per 30-second trial, so which is 72 joules in aggressive and 84 joules in balanced and 96 in performance. That's a 25% reduction in aggressive state and 12.5% in balanced. And the leakage term explains why alpha is 0.6 is the optimal lower bound. So below when there's a below that point, further reducing computation shortens the busy interval, but leakage is always active. So we can never stop the leakage current because leakage current is always utilized by the CPUs and other tasks. Even when there is a no task that's running, there is always a leakage current. So the energy savings per unit of quality degradation shrink. And coming to the third one, so critically, and this is what makes DAC better than any static alpha, any static utilization. So when rho arises above 0.87, the controller automatically restores full compute. So the energy savings are opportunistic, not unconditional, and then safety always wins. And coming to the next slide, challenges and design evolution. So we have made the 3 versions. So this first we have made the version 1. So I'll go to the each one. So our development went through the 3 versions and each one taught us something important about Linux scheduling in practice. So in version 1, so we use scheduling FIFO for all tasks with a static alpha, in which safety critical results were good, but NC and NC coefficient of variation was 12 to 31% from virtual machine wall clock inflation, and there's no runtime adaptation in this. So and then we built version 2. So in version 2 we have added a scheduling deadline for NC tasks to fix the CBS isolation problem and implemented the full DAC feedback loop in this. So in non-critical, coefficient of variation dropped to nearly 0. And then we discovered a critical inversion in this. So the critical inversion was found to be Linux always places scheduling deadline task above all the scheduling FIFO tasks in its scheduling hierarchy. So regardless of the first in first out priority number, our NC camera tasks were preempting the SC vehicle control thread. So the result was 293 to 450 vehicle control deadline misses per trial. So with coefficient of variance exceeding to 114%. So this is what we did in version 1 and version 2, and then we are coming to the final version, so that is version 3. So the final system, we applied scheduling deadline to all 5 tasks. So now EDF's deadline proximity rule provides correct SC and NC ordering. So vehicle control has 10 millisecond period, so its deadline always arrives before the camera's 100 milliseconds deadlines. So no explicit priority numbers needed here, and the ordering is formally guaranteed by the EDF theory. So moving on to the next slide, challenges at EDF co-activation and virtual machine jitter. So 2 more challenges worth explaining. So first one is EDF co-activation. LiDAR and radar both have 50 millisecond period with 2 tasks shared a period under EDF. So their deadlines co-expire simultaneously every 50 milliseconds, and the scheduler runs one while the other waits. So which inflates the waiting task response time by the first task execution duration. So this is why LiDAR and radar showed 13 to 23% coefficient of variance in the low trial, and importantly, this is known as a property of EDF with equal period tasks. So both tasks had 86% deadline margin and vehicle control was completely unaffected. And we have fixed. So the fix was like staggering their activation time by 25 milliseconds is a straightforward and planned for our bare metal evaluation. So the second one is like The VM jitter comparison table shows the before and after. So under scheduling FIFO, camera CV was 12.08%, under EDF CBS and it's 0.6%. So because CBS tracks CPU time rather than wall clock time. And moving on to the next slide, comparison to relative work. The comparison table shows our four approaches, which is RTDVS and DRA require kernel modifications. So, and we ran in the simulation. So grub-PA achieved 40% on ARM hardware. So we are particularly using ARM hardware with Linux. So grub-PA achieved 40% on ARM architecture, but requires kernel patches and ARM specific CPU frequency drivers for this. And DAC achieves 9 to 25% savings on commodity Linux with no kernel modifications and no DVFS settling delays. So which are 50 to 200 milliseconds and probability for our 10 millisecond control loop. And with a formally verifiable 3 states finite state machine, we can see here. So every result is reproduced from real hardware CSV data. We have executed, as I have said earlier, so we have executed version 1, version 2 and version 3. So for each version we have produced all real CSV data files. And so what I'm concluding here was like this CSV data was taken from our final version, so which is directly addressing the reproducibility gap that Bambagni et al. In our literature review he said that, so which is identified in the survey. So moving on to the next slide. So coming to the future work, so in the future work we can plan 3 more phases. So coming to the phase 1, which is bare metal Jetson AGX Xavier. So this gives us direct power measurement via INA 3221 current sensor. So this eliminates the hypervisor jitter. So now we are experiencing hypervisor jitter because we are executing this in our Parallels virtual machine and also in the architecture inside the Mac, and so this gives us more jitter, and we have reduced this jitter by using this DAC algorithm. But in the future, so we can directly put this in a bare metal Jetson AGX Xavier, which is a specific hardware to run this for the in automation vehicles, so which let us validate the energy model numerically. We also plan to implement the 25 millisecond activation staggering to fix the EDF co-activation CV. So coming to the phase 2, which is multi-core extension, the Jetson has an 8-core ARM architecture and a 512-core GPU. We want per core CPU monitoring and GPU offloading triggered by utilization transitions. And coming to the phase 3, which is the predictive DAC, dynamic alpha control, which is predictive. So instead of reacting to row changes to 500 milliseconds after they happen, we want to anticipate them from vehicle speed and sensor telemetry. So using a long short-term memory predictor, which is LSTM, and preemptive alpha transactions before load changes hit could yield an additional 15% savings. So yeah, and this is our future work. And coming to the next slide, so this is our conclusion. So I want to summarize this to you. The dynamic alpha controller is a closed loop, so which is a POSIX. This runs in the POSIX user space, and in POSIX user space feedback mechanism that automatically adjusts NC task computation intensity based on measured CPU utilization. So running on a pure EDF CBS architecture. So, and also I should mention that our 3 control trial produced 0 deadline misses across 13,208 jobs, and vehicle control CV at most of 0.033%, so which is a minimum 30 times safety margin, and non-critical task jitter improved 20 times through CBS isolation, and 9 to 25% energy savings with automatic rollback when load is high. And the development arc from version 1 through version 3 demonstrated real engineering. So we discovered a scheduling class hierarchy interaction that is often overlooked in theoretical treatments. So we fixed it and built a reproducible methodology for building EDF CBS on commodity Linux. So thank you for your time, and we are happy to take any questions.